This whole chapter is about linear relations, and it's a continuation of something you've probably been doing in math for 5 or 6 years, looking at patterns. So, for example 1, we have a couple of different patterns here. On the left, we have a pattern of squares, and you can see in figure 1, you have 3 squares, and in figure 2, you have 5 squares, figure 3, 7, and figure 4, 9 squares. So we're just adding 1 to the vertical row of squares, and we're adding 1 to the horizontal row of squares. The example on the right is a little different. We have a series of dots. So in figure 1, we only have 1 dot. In figure 2, it's almost like we add another row of dots below it with 1 additional dot. So we're adding 2 dots, and so we get a total of 3 dots. In figure 3, we add a new row on the bottom, and we end up with 6 dots. In figure 4, we add 1 more row on the bottom, and we end up with 10 dots. Now, one very important distinction about the kind of patterns that we're going to look at in this chapter is that we're only going to focus on linear patterns. And the example on the left is an example of a linear pattern. The example on the right is a nonlinear pattern. And how are we going to tell the difference between these? Well, let's take a look at the table where we have the figure number and the number of squares. So the difference between 3 squares and 5 squares is an additional 2 squares. And, as we said, we're adding 1 to the vertical and 1 to the horizontal. And we continue adding 2 squares as we continue down the table. So in every case, the figure has 2 more squares than the preceding figure. Let's compare that with the pattern on the right here. Going from figure 1 to figure 2, we added 2 dots. But going from figure 2 to figure 3, we added 3 dots, and then going from figure 3 to figure 4, we added 4 dots. Now, the characteristic feature of a linear pattern or a linear relation for this chapter is that we have all the same in terms of adding. When we go from figure 1 to figure 2 to figure 3 to figure 4, we're always adding a consistent quantity, or perhaps subtracting a consistent quantity. So this is an example of a linear relation. In the right, we start by adding 2, but then we add 3, then we add 4, and if we keep on going, we're going to add 5 and then 6. This is an example of a nonlinear. And these are very interesting, but we're not going to look at them in this chapter. So let's take a look at the example on the left with the squares. And the goal really is to write an equation that will help us understand what's going on with the number of squares. So let's take a look at the pattern here. So in figure 1, we go from 3 to 5 in figure 2. Now, one way to represent that is to say that we are adding 2 squares and starting with 1. So in other words, if we could kind of go back to figure 0, we'd really only have 1 square. And then every time, we just simply add 2 more squares. So figure 2, we have 2 times 2 plus 1. And figure 3, we have 2 times 3 plus 1. Figure 4, we have 2 times 4 plus 1. And you can see that the numbers line up perfectly. So for figure 1, 2 times 1 plus 1 is 3. For figure 2, 2 times 2 plus 1 is 5, etc. So the number in the brackets is just the figure number. So we're basically relating the set of numbers on the right to the set of numbers on the left. If we continued this on out to some arbitrary figure number, and that is usually represented with the variable n, we could say, well, we don't know what that number is, but whatever that number is, it's going to be 2 times that number plus 1. And this is the equation that represents the number of squares for any given figure number. So for instance, we can use this to find the number of squares in the 10th figure. So the number of squares in the 10th figure would simply be 2 times 10 plus 1. So we'd have 21 squares in the 10th figure. We wouldn't have to follow that pattern down or draw out all 10 figures. We could go much further than this, obviously. We could say, well, what's the number of squares in the 100th figure if we continued this all the way out? So the number of squares is equal to 2 times 100 plus 1, and that would be 201. Okay, so let's take a look at another example, this one perhaps a little less abstract, and that's the conversion between Celsius and Fahrenheit. So Celsius and Fahrenheit are two different ways of measuring temperature. Some countries, like the United States, still use Fahrenheit, so if you're looking at a weather forecast, you'll see the temperature listed in degrees Fahrenheit. Most countries around the world have adopted the metric system, which is using degrees Celsius. So we can make a little table to show the conversion for any temperature in Celsius to any temperature in Fahrenheit, and I've got a few temperatures here. So 0 degrees Celsius, which is the freezing point of water, is the same as 32 degrees Fahrenheit. And then as we go up to 1 degree Celsius, we go up to 33.8 degrees Fahrenheit. So we're just adding 1.8 degrees. As we go to 2 degrees Celsius, we go to 35.6, which is an additional 1.8. And 3 gets us to 37.4. So again, we're adding an additional 1.8. And then we just keep on adding 1.8 every time we add a degree Celsius. So you can see that we're adding the same amount each time. So this is an example of a linear relation. So can we come up with a formula that will allow us to convert degrees Celsius to degrees Fahrenheit without having to make up a big table like this? Well, again, the key is to look at how much the degrees Fahrenheit is increasing every time you increase the degrees Celsius by 1. So we're increasing by 1.8. So whatever the difference in Celsius, we're multiplying that by 1.8. And we need to also figure out, well, where are we starting from? So, for instance, at 0 degrees Celsius, we still have 32 degrees Fahrenheit. And when we add 1 degree Celsius, we add 1.8 degrees Fahrenheit. But we go from 32 to 33.8. So you can think of 32 as the kind of starting point, if you like. And so we end up with a nice little formula here showing the relationship between Fahrenheit and Celsius. Fahrenheit, or the temperature in degrees Fahrenheit, is 1.8 times the temperature in Celsius plus 32. So we can ask a question like, what's the temperature in degrees Fahrenheit when the temperature is 20 degrees Celsius? And all we have to do is plug the appropriate numbers in. So 1.8 times 20 plus 32. And 1.8 times 20 is 36. 36 plus 32 is 68. So the temperature in degrees Fahrenheit is 68 degrees, and that's equivalent to 20 degrees Celsius. All right, so let's take a look at another example. Let's say that you're going to take a taxi cab ride, or in Vancouver at some point in the hopefully not too distant future, an Uber ride or a Lyft ride. Now, most of these cab rides or ride shares have a fee structure that has a base fare. So the minute you walk in, the minute you sit down in the car, you actually have a dollar amount on the meter. So let's say, for example, you have a $2 base fare. And then the fare is usually charged on a per kilometer or per minute basis or some combination of that. So let's keep it simple and just say, for example, that the fare, the additional fare is $1.50 per kilometer. So we can make a little table and figure out what the cost is going to be for a particular distance ride. So the distance, D, is in kilometers, and the cost, C, is in dollars. So for a 0 kilometer ride, even though obviously we would never take a 0 kilometer ride, we're actually still paying $2. For a 1 kilometer ride, we're going to pay $3.50, and we get that because it's the $2 plus the $1.50. For a 2 kilometer ride, it's going to be $5, and again, every additional kilometer is going to cost you an additional $1.50. For 3, it's going to be $6.50. And for 4 kilometers, it's going to be $8. And you can see that this is like the other two examples. We're adding the same amount each time, so this is a linear relation. So we can come up with a formula, and the formula is the cost is equal to, and again, look at the amount that is being added each time. That's the amount that the cost is changing when you change the distance, in this case distance, by 1 unit, so by 1 kilometer. And that's the amount that we're essentially magnifying that distance, that difference by. So we have 1.5 or 1.50, we can drop the final 0, times the distance plus that base fare of 2. So now we can answer a question like, well, what if we get in, what if we have to go 12 kilometers? So how much is a 12 kilometer trip going to cost? Well, we can use our formula. The cost is going to be 1.5 times 12 plus 2. 1.5 times 12 is 18. 18 plus 2 is 20. So the cost for a 12 kilometer trip is going to be $20.